Hi there, Mr. Sutton, bringing you the first in a series of 3 lessons on transformations, this one on reflections and symmetry. So we'll be performing reflections on graphs of functions, and we'll also test for different types of symmetry. Transformations are one of those mathematical topics that you actually see every day without even knowing it. Mario, for example, wouldn't be able to do too much without transformations. If you want Mario to turn around, you're going to need to know how to do reflections. If you want to make him run and jump, like so, you need a translation. If you want him to somersault in the air, well, that's a translation and a rotation. And if you want him to change into Super Mario, you need a dilation. We're only going to talk about translations in this lesson, but this seemed as good a place as any to talk about how awesome transformations are. So let's dive right in and do some reflections. Now, all transformations involve adding or multiplying some constant to x or y or both. Reflections all involve negating the output or the input. If we have negative f of x, what that means is we're applying the function first and then multiplying the output by negative 1. So we're multiplying all the y values by negative 1 in this case. Which means if you're negating all the y values, you're flipping everything over the x-axis. So let's pick some corner points and go ahead and do that. So this point, for example, gets flipped up here. This point comes down here. Here's another corner. That'll go down here. This corner gets flipped up, and this point can go back down. And then just connect the dots. Now we saw in the last example that changes outside this f of x function affect the vertical of the graph, the y values. Changes inside affect the x values. This here is multiplying all the x values by negative 1. So let's go ahead and do that. And by the way, if we're multiplying x's by negative 1, that's going to flip us over the y-axis. That's a horizontal flip. So this point is going to move all the way over here. This point moves to 2 this way. This point on the y-axis stays right where it is. This point flips over here, and this point's going to flip back here. Connect the dots, and there's our reflection. Now, just looking at this as one big graph, with the old graph and the new graph both in there at the same time, take a sec and reflect what kind of feature this whole graph would have. You think you have it? That feature, closely tied in with reflections, is symmetry. Symmetry is when you're able to match up parts of a shape by folding it over an axis of symmetry or by rotating it around a point of symmetry. There are 4 major types of symmetry we're going to look at. One of those is x-axis symmetry. So here's a graph that has that kind of symmetry. Let's say you have the point 2, 1. That means you could match it up with another point on the other side of the x-axis just as far away, 2, negative 1. In general, if you have x, y on the graph and x, negative y, you've got x-axis symmetry. Y-axis symmetry is the same idea but over the y-axis. So here's a graph like that, nice little absolute value graph. By the way, this first one was not a function. This next one is. So let's say you have the point 3, 2, then you have the point negative 3, 2 on the other side. So if you have x, y and negative x, y, then you've got y-axis symmetry. Now the line y equals x is another good one to have symmetry over. Here's a function that has that kind of symmetry. And here is the line y equals x. It's just a line with a slope of 1 and a y-intercept of 0. So if we have the point 1, 4, we also have the point 4, 1. In general, if you have x, y and y, x on the same graph, you've got y equals x symmetry. And last but not least, there is origin symmetry. Here's a graph that has that. So if you have the point 1, 2, then if you were to rotate this, you would get a matching point down here of negative 1, negative 2. Now taking a look here, that means if you have x, y and negative x, negative y, you've got origin symmetry. And origin symmetry, you could almost think of it as flipping it over the y-axis and the x-axis in one shot. Now, you might be thinking, well, I kind of understand the different types of symmetry. You know, if I have a picture, I can tell what kind of symmetry it has without worrying about it further. But what if you don't have a picture? What if you have this equation here, and, I mean, you really can't easily graph this, so you still need to figure out what kind of symmetry this has without a graph. Fortunately, there are some tests we can run to see just that. So let's say you want to test for x-axis symmetry. To test for any kind of symmetry, you have to plug in the right things for x and y. To test for x-axis symmetry, since x comma y and x comma negative y are both on the same graph, you have to plug in negative y for y in the original expression. So instead of writing x squared plus xy equals 4, we would write x squared plus x times negative y equals 4. And then once you've done that, simplify it and see if you get the original equation. If you do, then you've got that type of symmetry. If you get something different, then you don't have that type of symmetry. So if we simplify this, we can write this as x squared minus xy equals 4. And that is definitely different than what we started with. There's no way to make this and this the same. So we would say we do not have x-axis symmetry. Now you might be thinking, well, that's kind of annoying, plugging in variables for variables. Why don't I just plug in a point that I know is on this with a negative y instead of a positive y? And I mean, you can use individual points to disprove symmetry, but you can't use them to prove that it has a type of symmetry, because you might have just gotten lucky. So you really do need to use variables when you're doing these tests. Let's try the y-axis test out. So for this one, instead of doing negative y for y, we have to do negative x for x. Notice that the x and the y are kind of counterintuitive. To test for x-axis, you need negative y. To test for y-axis, you need negative x. So we've got, instead of x squared plus xy equals 4, we have negative x squared plus negative xy equals 4. Now be careful with your order of operations. This is going to be inside of parentheses so that when you square it, this still comes out to positive x squared. This, however, is going to be negative xy just like we had over here. So we actually end up getting the same result, and this does not have y-axis symmetry. To test for line y equals x symmetry, since x comma y and y comma x are both on the graph if it has this kind of symmetry, you're going to switch x and y. Wherever you see an x in the original, you put a y there instead, and vice versa. So this is going to get rewritten as y squared plus y times x equals 4. Now this yx, we're just going to write that as xy. We always put it in alphabetical order. So this term actually stays the same. However, this is y squared instead of x squared, and there's no way around that. This does not have y equals x symmetry. For the last one, you might remember that for origin symmetry, the points x comma y and negative x comma negative y are both on there. So we're going to make x and y both negative. Pause the video and take a sec to run this test yourself. Okay, let's see how you did. So we're going to write this as negative x squared plus negative x times negative y equals 4. Negative x squared we saw up here is really just x squared. And here we have a negative times a negative. So this comes out to positive xy. And then 4 is just 4. Comparing this to the original, that is exactly the same as what we started with. So we actually hit gold on the last one. We do have origin symmetry on whatever this weird shape looks like. So that's it for our discussion of reflections and symmetry. Join me next time when we talk about dilations. Until then, this is Mr. Sutton signing off.